brought the same. Sometimes they don't happen that I love them. Still need one more bus here. Okay, it's up to you.
MS-TAS 2018, 12. Mimarlıkta Sayısal Tasarım Sempozyumu, tematik sunumlarından kinematik ve robotik mimarlık tasarım başlıklı sunumunu gerçekleştirecek olan Sayın Doktor Yan Suci'yi sahneye davet etmeden önce hocamızın özgeçmişi hakkında bilgi vermek istiyorum. Doktor Yan Sucik, Gdańsk Teknoloji Üniversitesi Mimarlık Fakültesi Şehircilik Bölümü, Mimarlık ve Sulak Alanlar Bilim Dalı'nda görev yapmaktadır. Mimaride kinematik, mimari tasarımda dijital teknikler, dijital üretim, mimarlık ve sanatta yapay zeka formları üzerine araştırmalar yürütmektedir. 2011'den beri karmaşık iç mekan tasarımları, konut yapıları, kamu yapıları, yatırım projeleri ve görselleme çalışmaları üzerine yoğunlaşan kişisel bürosunu yönetmektedir. Çalışmaları Polonya ve uluslararası platformlarda ödüllere layık görülüp sergilenmiştir. Ayrıca araştırma aktivitelerinin bir parçası olarak mimari enstalasyonlar hazırlamaktadır. Sunumunu gerçekleştirmek üzere Sayın Dr. Yan Suci'yi sahneye davet ediyoruz. We invite Dr. Yan Suci to make the thematic presentation titled as Kinematic and Robotics in Architecture Design.
Hello, thank you for inviting me. It's really a pleasure to be here, and at this point I would like to thank especially Ilker and Berke and Mehmet for taking such a good care of me through the whole journey and preparation for this event. I will start with some thoughts. While I was coming here, I was thinking about talking over theoretical aspects of kinematic architectures, mainly. And when I came here to the building and I've seen what you've managed to do and talked with students and professors who work on them, I thought it's going to be much more interesting for you to hear and listen a little bit about our experiences in building one-to-one prototype models and working with architecture while building it and trying to accomplish something from basic materials with understanding the whole process of building a form. And with this topic, it's very important for me to note that I'm not working as an individual on this matter. I'm working in a group with Robert Juchniewicz and Kacper Radziszewski, who are my colleagues from Gdańsk University of Technology, and most of the constructions that will be shown were built together by us or in a group of two, depending on the subject and time, of course. I will explain and describe six ideas. The first one would be the parametric dome. This was the second dome that we managed to build. Then I will move to parametric tunnel, and I will show you also the wall and an installation made of copper pipes. And then we will move to something more complex in the way and based on the marching cubes idea. And I will finish up with a parametric shell system that we've managed to work on. The first concept is work that we did with students as an elective class, and the idea was to prepare a form that would stand out with its quality of architecture and the way it was designed. And at the beginning, we've started with a dome structure, and based on this dome, we've worked on the planarization of the form. And thanks to optimization in Rhino, Grasshopper, and Kangaroo, we've managed to planarize the hexagonal elements to make the form flat. At the beginning, we've started just with cardboards, and we had a few sheets just to cut with laser cutter the test model. That was very important for us. And then we've used the plywood and chest hinges to create the form. This is the early example of what we've started. The red form is the starting dome that we've worked on, and the gray one is already one that has been planarized with Kangaroo. And while working on this idea, we've noticed while checking its construction that it's going to be very hard to stand. So we've decided to make it lighter and get rid of some parts of the panels while keeping their structural integrity. So this way they were divided just with Voronoi pattern, but it was calculated the way that the frames were good enough and solid enough to handle the whole form. Afterwards, when we started working, we needed to check everything, and we had some problems in the back of the form. However, at the end, it ended up nicely. This is the test model that we started. At some point, we wanted to create a light form inside, and we wanted also to play with light, but then, due to the changes in the form, we decided not to go there, and this shows also a very relevant and important element. This was a 5th or 6th structure that we've built at the time, and we thought we knew everything about buildings form like this, and at some point it happened that the bottom of the structure was not planar. We've planarized everything besides the thing that should be planarized at the very beginning, so the platform where it should stand. Then, thanks to this small model, we've managed to change it, and the final elements were already planarized. We had them cut outside of the university. They brought them to us, just like this. And then the whole structure was being built. This is the picture of the actual structure that was built at the Faculty of Nanotechnology in Gdańsk University of Technology. And it stood there for about 2 months, and it's shown the possibilities of changes in modern contemporary architecture. An important feature of the form was the play of the light, because we knew we had a very good lighting inside, and we could have done something with it. That's why also this perforation happened, to make it more diverse in the form and to actually build. And this was one of the examples that also show something which we as architects not always think of. When we analyze forms in terms of structure, we analyze the main material. We very often forget about small details. And what happened here is that hinges and connective elements were as heavy as the whole form. At the beginning, we didn't check it, and we needed to double check it afterwards. However, at the end, it ended up quite nicely looking, and we were glad about the final result. The other idea is based mainly on the same principle. However, there was no planarization in this concept. It was straightforward, the geometrical form that we've started. There was idea to create a tunnel near the forest. It was done with plywood, and it was a part of a summer school concept that we do, based on entirely one material. So all the connectors, all the materials were done from the plywood. This plywood was about 4 millimeters, so it was very thin. And with this patterning, we wanted to create a diverse feeling of the form. This is a partly done form presented in here, and this is how we thought it should look like at the beginning and how it actually ended. Yeah, we wanted to create something in the natural environment that would, in the same time, stand out and somehow became a part of it. But here, the most important part of the process was actually the optimization of the form, because whenever you're trying to build something that is irregular, there's always a problem of the loss of the material, because you're losing a lot. And here we've managed to squeeze them, having about 15% loss of the material. So this is as if it was a very regular form. Thanks to the Rhino nest that we've used, we managed to really optimize the whole process from the very beginning. And everything, even the connecting elements, these small ones that are in here, were placed on the boards. So then, also with the time of manufacturing, because whenever you're manufacturing stuff, if you do it automatically, sometimes it happens that, for example, CNC machine starts in the left corner, then goes to the right, then to the bottom, and to optimize this path, it goes straight to how efficient you can be and how fast you can build things and how much you can save on the whole process. And this was the main challenge of this design. It was not the form, but the optimization of the whole process. Yeah? This is how it looked from the side and from the entrance. It was a little bit too narrow for people to cross, but we actually didn't want people to go inside of it. Yeah? It's always a bit risky with forms like this. During the same workshop, another form was built, and it has been done also with plywood, but in a different idea. Here, the main idea was to create a few elements that were the same. So we had these discs that were exactly the same, and the only differences were in here with these elements. We treated them as a rigid body in a concept, so when it was created throughout the script, it started as a plane model, and then when it got thickness, the whole structure started to change its geometry rapidly with a kind of an automatization in the process. Yeah? This way, we managed to accomplish not only the wall, but also the connection system that was based on one material. You can see how it goes in here. So it didn't need anything else. It was self-standing, self-sufficient element that was built just by connecting these elements. We've also tried working with some metal panels that were also cutted. We only did a few examples just to check how it would look like, because it was a little bit time-consuming to cut them out. And this is the part of the whole structure, a part of the wall that was created next to a tree in the forest, and how it stood. What was also important in here, we tried to make it as light as possible so that it could stand on 2 or 3 elements. At the end, it stood only on 2, and it managed to do that. The next one is quite interesting because of mixture of techniques. Building this one, we've decided to start not with the form. We've decided to start with idea how we could build something that hasn't been built before. And there are many concepts of printing out 3D houses or printing out big structures. But each and every time, the concept was to print everything from the beginning. And we thought, how about mixing 2 techniques? So if we could print out the connecting elements, these are the white ones, and then just organize other elements in a traditional manner. This way we could work in bigger scale and make it look much better. This was done in Sopot's college, and it was also a part of parametric workshop that we've held there. And what was unique in there, that each element, each joint was different. So we had 36 joints, each was different, and each one of them was named in the corner. So we knew exactly which pipe to connect to it, and the pipes were also numbered. The assembly of the whole element, the structure, with no plans at all, the only thing that the students were given for the assembly were actually the numbers on the pipes and the numbers in these elements. So you didn't need any drawings, and this is relevant for most of our concepts. For the structures that you have seen, we've never prepared any traditional plans, any traditional drawings. There were just the instructions. Most of the instructions were done in Excel file. So there was even no line at all in the instruction. There was just how to connect elements and how to build. And this is also something that is happening. If you look at the work of Himmelblau or the concepts of Zaha Hadid, how they build their facades, or the marvelous idea that Morphosis with Tom Main did in Paris on the concept in the building in La Défense, where the whole building, the whole structure of the building was dated with days and hours of actually putting them on the building. Yeah? The project wasn't finished. However, the idea to completely change the process of building was something that triggered us into changing the way we thought about the architecture, and this was one of the examples how we worked with the copper pipes. And here there's also something interesting about these copper pipes. They are all numbered, as you can see in here, but at the beginning, when we checked the amount of elements that we needed, it happened that we needed 25 elements to cut them. And then we thought that we are optimizing everything from the very beginning of what we've been doing. And we started optimizing the size of the pipes and the way they were connected in this way that it would not affect the form. We've created a special script in Grasshopper that shown us with green and red elements where we had the problem. Whenever there was something red, showing us in the view. We knew that we need to change the geometry a bit, and this way we've managed to decrease the number of copper pipes from 25 to 20. So it was about 20% less material needed for exactly the same form. If you use it on the small scale, this is nothing, but if you compare it to building real architecture, when everything goes into millions, this is huge. If you can do something like this with any facade that you are working on, this will make you be the one to be chosen for the project, possibly. Yeah? And these are the joints. They were numbered here. It's a little bit hard to see from the side, but each and every one of them was numbered. This is the assembly process. What was hard? This was a self-standing structure. So to put last 2 or 3 of them, it was all very strict. So we encountered some problems. We even needed to cut one pipe a little bit, like 2 millimeters, just to make it fit on the side. However, at the end, it did fit, and it stood like this for a year, with people going next to it, taking pictures of it, walking into it. So many accidents happened to the form, and it was quite good in this term. However, what was noticeable, these elements, the joints, if you know the 3D technique of printing, it starts with the layers. So you do the first layer, then the second layer, third, and so on. Yeah, it's basic stuff. But what is the problem of layering? Whenever you are layering, the material is not strong in this direction. So while printing these 36 elements, we needed to prepare a good technique to print them in the way that they wouldn't have this weakness in the most important parts. Because if we would encounter weakness, for example, in here, then possibly the structure could collapse. Yeah? And we managed to do this just like that. What was interesting, the structure itself could have been done without any glue or no connection. It was so accurate that we needed just to put them inside. We used the glue, of course, even though we didn't need to, but just to be safe, because it was in the environment that was not controlled by anyone, and we didn't want anything bad to happen to somebody who would just play around it. But it ended looking like this, with a kind of a nice opening form. The most challenging part was the connection of these 2 elements, because as you can see in here, this is the frame, this is the outside, and this is the inner space. This is like 2-layer structure. So the inner structure, when it connected to the outer, the joints, this one is actually 3, but some of them were 5 elements. And to create the joint with 5 elements with every different angle, you needed to be very accurate. And any minor mistake on the process of creating the form could have completely lost the whole process. And printing them was 3 weeks for 2 printers for about 20 hours a day of printing. So you can imagine the time of printing. And first, when we've counted the printing with Grasshopper, it said it's going to be about a week. But then printing was a little bit slower. We needed to be more accurate, get the layer a little bit smaller as well. And all these things that happened make the printing time 3 times as long as we expected this. And this is what happened. Whenever you're doing a prototype that you've never built before, the problems occur in the places where you wouldn't expect them to be. While doing this, we had a huge experience in printing, in 3D printing. We've done plenty of stuff. We did a test model. We've printed several of them just to count the time, to be as precise as possible. And in the end, human mistakes, some minor problems in the process, lack of filament, and other things uncounted 3 times the time of the printing. However, the detail was very nice and sharp. It looked quite good, I must say. And this led us to another example, just the same year, actually. We thought that it would be good to build something in a different way, because while building and creating things of our own, it's much easier, because you can do whatever you want and however you want it. Here, we've decided to work with 2 elements. We've ordered small boxes and big boxes. These boxes were made of styrofoam, and they were 20 by 20 by 20 and 10 by 10 by 10. And the whole process in here was based on 470 big cubes and 360 small cubes. The whole height of the structure was about 540 centimeters, and the volume was over 4 meters, so it was large. we started with a small examples of connecting these elements, because what was the problem? How to connect these elements if we didn't want to use the traditional technique that you would use to put the styrofoam on a house. Yeah? And we didn't want the connection to be visible. So we tried several glues, and none of them work. At the end,